So we have the heat, the 859.5 kilojoules that were required in order to sublimate the whole thing, because that's just delta E bond. So that's Q here. Do we know what temperature this occurs at?
Negative 78 degrees Celsius.
Yeah, so can we just put in negative 78 degrees Celsius in the denominator here?
Yes.
Except for one thing. This is not a delta temperature, this is the temperature. Yeah, this has to be in kelvins, right? Anytime, if it's a delta temperature, you can use Celsius or Kelvin as long as you're consistent about it. But T without a delta attached to it, that has to be in kelvins. So you convert this to kelvins by adding 273, and yeah, that should be 194. Is that 194? I think that's 195, isn't it? 78, or 273 minus 78, yeah, it should be 195. So 195 kelvins is the temperature at that this occurs at. So we divide those, positive 895 divided by 195, and I'm getting about 4.41, positive 4.41. And the units there would be kilojoules per Kelvin. So that then would be the change in entropy associated with this process. Sublimating the dry ice involves increasing the entropy by 4.41 kilojoules per Kelvin. Any questions on that so far? And then if we want to plot that on an energy versus temperature graph, we can draw out this graph. Let me set up some axes. So let's say we've got entropy and temperature. And typically the horizontal axis is going to be entropy in units of, let's say, kilojoules per Kelvin. And then the vertical axis would be temperature in Kelvin. So what we would do here is we could mark the initial and final situations. And note that during this process, what's not changing? Yeah, the temperature is not changing. So we're going to have some initial value, which is, and since entropy is increasing, our initial value is going to be low entropy and our final value is going to be higher entropy. But it's all going to take place at the same temperature. So this path then, the process is just going to be a flat line from the initial situation to the final situation. So something like that. Let me make that a little narrower. So there's our process. We're going from initial to final. Let me label those initial, final. And it's an isothermal process. Isothermal in the sense that the temperature is not changing. So on a temperature entropy graph, an isothermal process is a horizontal line. By the way, what would an isothermal process look like on a pressure volume graph? If the temperature is not changing, what would the pressure volume diagram look like? What sort of shape would that be? Yeah, it's going to be a curve. Specifically, it's going to be a portion of a hyperbola. So these graphs look very different. It's still representing the same process. This isothermal process on a pressure volume graph is going to be actually that's not entirely true. The pressure volume graph, that curve assumes that it's a gas the whole time. This is a phase change, so that's not really going to be relevant. So the pressure volume graph is going to be rather different in that case. But in general, an isothermal process on a temperature entropy graph is always going to be a flat line because temperature is remaining constant. And let's see if we can label these. We know the temperature at least. We can label the temperature here The temperature at which this whole process occurs is, what was that? 195 Kelvin. And then we also want to label the entropy, starting and ending entropy. So we've got the initial entropy, and we're also going to have the final entropy. And we can't really calculate the actual values of entropy. We just can calculate the change because we have a formula for delta entropy. So we know these are 4.41 kilojoules per Kelvin apart from each other. And so it has to give us an initial value of entropy. So in this case, we're calling the initial entropy 4,800, although that's in joules per Kelvin. So let me change the scale here. 4,800 joules per Kelvin. And then how do we figure out the final entropy? Yeah, we'd add the 4,410 because we could convert that. We originally wrote it as joules per Kelvin. We can absolutely rewrite that as, or sorry, kilojoules per Kelvin. We can rewrite that as 4,410 joules per Kelvin. So we fill that in. 4,800 plus 4,410 would be 9,210. So the final entropy would be 9,210 in joules per Kelvin. So we now have all the important markings we need. We've got 195 kelvins of temperature at the whole process. The starting entropy, we're calling 4,800 joules per Kelvin as just a reference point. The final entropy is 4,410, higher than that, so 9,210 joules per Kelvin. So that would be a well-labeled graph of this process. And it has to be a straight horizontal line segment because what's not changing during this process? Yeah, no change in temperature means no up or down motion on this graph. We're just moving to the right as entropy increases because we're adding heat to the system, but we're not changing the temperature because it's only a phase change. And then show that the amount of energy transferred as heat is the same as the area under the curve. How would we calculate the area under the curve here? If we're talking about this area under the curve all the way down to the axis, how would you calculate that area? Yeah, area equals base times height, which will be, and yeah, that's going to equal the base here. We got to be careful though. The base isn't, this width here is not the amount of entropy. What would you call this width? That's not just how much entropy there is. That width is the what? Yeah, that's how much change there is. So the base is the delta entropy. And then the height, what would you call the height on this graph? Right, that's just the temperature. So the area is just going to be delta S times temperature. And we could fill in the values for that. We could say delta S is 4,410 joules per Kelvin, and temperature is, what was that? 195 Kelvin. And those are going to multiply out to the amount of heat added anyway. But we can also look at this more algebraically. How do we calculate delta S in the first place? Right, that was a Q over T in the first place. So delta S is Q over T times T. T's cancel out, all we're left with is Q. So algebraically, it makes sense for the heat to represent the area under the curve. And so far, we've just shown that's true for a rectangle if the curve is a flat horizontal line. But it turns out this is true in general. No matter what the process is, no matter what shape the curve is, on the temperature entropy graph, the area under the curve all the way down to the axis represents the amount of heat transferred. Also, were we adding heat or removing heat to make this happen? Yeah, we had to add heat to make this sublimate. And that corresponds to entropy increasing or decreasing. Yeah, or I would say delta S is greater than 0. The entropy is always positive, just based on the way we define it. You can't have negative entropy. But the important thing is that the change in entropy is greater than 0. So in general, if conceptually we can say if heat enters the system, then entropy increases. And we can write those as inequalities in terms of positive and negative. If heat is positive, then delta entropy is positive. And that also works in reverse. If heat leaves the system, then entropy decreases. In other words, if heat is negative, because heat being a negative value means heat is leaving the system, then delta S is also negative. So you can tell that from, or you can see whether heat is entering the system or leaving the system, whether heat counts as positive or negative, based on whether entropy is increasing, going to the right on the graph, versus decreasing, going to the left on the graph. So if the process is an arrow pointing towards the right, even if it also has some up or down component, anything to the right means that we're increasing entropy and therefore heat is being added to the system. Whereas if the process is pointing towards the left, that means we are decreasing entropy, so heat is leaving the system. So the area under the curve tells you how much heat. Whether the process is to the right or to the left tells you whether heat is entering or leaving. Any questions on that so far? And also in part E, it's talking about absolute, it's kind of an unusual use of absolute value. It doesn't mean take the value and make sure it's positive. This is just talking about the actual value as opposed to the change. Like for instance, the absolute value of temperature is the 195 Kelvin. Did we use that 195 in our calculations? Yeah, that was definitely used for calculating delta entropy. We took the heat and divided by that temperature. And we couldn't have just set an arbitrary value there. For instance, if we use Celsius, then 0 is kind of arbitrary. And so calling it negative 78 degrees would give us the wrong answer. So we can't just arbitrarily set a reference point for temperature. Temperature has to be the actual temperature in kelvins, because kelvins actually means something. Kelvins is how far you are above actual absolute 0. It's not just how far you are from some arbitrary reference point. What about the entropy? It tells us in the problem that the initial entropy is 4,800 joules per Kelvin. Did we use that 4,800 joules per Kelvin in our calculations? No, we didn't actually need that, right? The important thing is not how much entropy there is. The important thing is what? What value about entropy did we use in our calculations? Yeah, the 4.41 kilojoules per Kelvin, or 4,410 joules per Kelvin. Because that's not the entropy, that's the 4,410 joules per Kelvin. Yeah, that's exactly, that's the change in entropy. And note that that's exactly the width of the rectangle here. the width of this rectangle is the change in entropy. It doesn't matter what the entropy is. It doesn't matter how much empty space there is back here on the left side of the graph. The important thing is the change in entropy, because that change in entropy is the width of the rectangle. But the height of the rectangle isn't the change in temperature. The height of the rectangle is the actual temperature. So the area of the rectangle, and therefore the amount of heat, is determined by the actual temperature and the change in entropy. So for these purposes, you don't need to know how much entropy there is. You just need to know how much it changes during the process. So I think that's the distinction part E is trying to make, that for temperature, the actual amount matters. For entropy, all that matters is how much it's changing. And the similar is true on a pressure volume graph. If this were a pressure versus volume graph, the actual amount of pressure would matter. But for volume, all that matters is the change in volume, because that determines the width of the rectangle. Any other questions on that so far? Or anything else you want to work on? Sure, let's take a look at question 4. Let me clear this. And then question 4, we're looking at two objects that are exchanging 10 joules of heat over a short period of time. And we're looking at two cases. In both cases, object A is colder, but object B might be a lot hotter or only a little bit hotter. And we're assuming they're only exchanging energy with each other because they're insulated. And they're so large that they're not changing temperature very much. So let's say that the 10 joules of energy is only enough to, not really enough to make their temperatures change significantly. Maybe object A warms up from 300 to 300.001 or something. And object B cools down from 301 to 300.999. So we're assuming that their temperatures don't change enough to matter very much. And we want to figure out the changes in entropy during this process. So in this case, what formula could we use for change in entropy? We would generally use that logarithm formula, the delta entropy equals heat capacity times logarithm of, and I wouldn't call that TB over TA, I would call that T final over T initial, because we're not talking about the temperatures of A and B, we're talking about the final temperature of one object and the initial temperature of that same object. We're looking at the ratio of initial and final temperatures. The thing is though, this formula is perfectly accurate if the temperature is changing. However, what do we know about the temperature change in this process? How much are the objects changing temperature? Yeah, they're not changing temperature very much, not even enough to really notice. Because keep in mind, we're not waiting for these to come to thermal equilibrium. We're not putting them together and waiting until their temperatures meet somewhere in the middle. We're putting them together, allowing them to exchange a tiny bit of heat and then separating them again. So we're not actually allowing them to change temperature in a significant way, which means this formula is not going to be as useful, especially since we don't have their heat capacities anyway, and we don't know how much the temperature is changing either. So instead, I would use heat over, strictly speaking, it would be heat over T average. But since the temperature is hardly changing at all, we can just treat the 300 Kelvin as the average temperature of object A. And in case 1, 350 Kelvin as the average temperature of object B. Whereas in case 2, we'd say 301 is the average temperature of object B. But it's not changing enough to really matter. So I would go ahead and use this formula because the temperature is not changing in a significant way. And we don't even have the heat capacities anyway. But we do know how much heat is being exchanged. So let's take a look at these one at a time. Let's say in case one, we want to calculate delta entropy for A, and also delta entropy for B. And then we should also calculate delta entropy total once we've got those. So how would you calculate, let's say delta entropy for A? What's the heat for A? The 300 Kelvin would be the temperature, but what's the heat that it's gaining or losing? How much heat is being transferred? Yeah, 10 joules. And would we treat, for A, would we treat that as positive 10 or negative 10? Is A gaining or losing heat? Yeah, positive. So positive 10 joules over 300 Kelvin, which is about 10 over 300. That's 1 over 30. So 0.0333 joules per Kelvin. And that's a positive because it is gaining heat. What about for object B? What's going to be different there? Yeah, since B is losing heat, we would write its heat as negative 10 joules. Heat is leaving object B and entering object A. So for object B, we've got negative 10 joules divided by what temperature? Right, 350 Kelvin. So we divide those and we get negative 10 over 350. And I'm getting about 0.0286 joules per Kelvin. So that means A is gaining entropy, B is losing entropy. By the way, is it possible for an object to lose entropy? I mean, it should be. It's certainly happening for B. Losing entropy just means heat is leaving the system. But let's relate that to the second law of thermodynamics. First law of thermodynamics is just conservation of energy. Delta U equals heat plus work. But the second law is somewhat more complicated. Second law of thermodynamics has to do with entropy. Specifically, what does it say about entropy? Have you seen the second law of thermodynamics yet? Yeah, specifically the change in entropy is greater than or equal to 0. Entropy is positive by definition, but the second law of thermodynamics is talking about the change in entropy and says the change in entropy must be greater than or equal to 0. In other words, entropy can increase or stay the same, but cannot decrease. However, that doesn't apply to everything. For instance, object B is definitely decreasing in entropy. We don't want to say that nothing can decrease in entropy because object B is decreasing in entropy. Second law of thermodynamics really only applies to what sorts of things? Well, we're not talking about energy here, though. We're talking about entropy. And entropy, it's kind of related to energy in the sense that we're changing the entropy here by having heat flow. But the second law of thermodynamics, like let's say you want to decrease the entropy of something. What do you have to do to an object in order to decrease its entropy? Yeah, you've got to take out heat. Are there any situations where that can't happen? How would you set up a system where it's impossible for heat to leave? Yeah, a closed system. The second law of thermodynamics specifically applies to closed systems only. In any closed system, the total delta entropy is greater than or equal to 0. The total entropy of the system can increase or stay the same, but cannot decrease. That's the full second law of thermodynamics. It only applies to closed systems. Is object B a closed system? Or what's it interacting with? Right, object B is interacting with object A. So it's certainly possible for B to decrease entropy, and in fact it does, because it's interacting with something else that's increasing entropy even more. If we want to apply the second law of thermodynamics, we should look at the whole system, because A and B together form a closed system. And in fact, if we take a look at the total delta entropy, how would we find that? Yeah, we add those changes together. Delta SA plus delta SB. So 0.0333 minus 0.0286. And I'm getting about positive 0.0047. So it looks like entropy is increasing overall. B is losing entropy, but A is gaining even more entropy. So the total entropy of the system, and therefore the total entropy of the universe, is increasing as a result of this process. In general, anytime objects are approaching thermal equilibrium, even if they don't get all the way to thermal equilibrium, these objects are approaching thermal equilibrium. They're exchanging heat with each other in a natural way. That's going to result in an increase in overall entropy. So there's not really a law of conservation of energy. In a closed system, total entropy does not have to stay the same. It could stay the same or it could increase. It just can't decrease. Any questions on that so far? Then let's take a look at case 2. And see what's going to be different. I think we can probably reuse a lot of the framework we've got here, because this is still overall the same sort of system, same sort of setup. We're just looking at different values. Actually, is A going to be any different? Yeah, A should be the same, right? A is still gaining 10 joules of heat while it's at 300 Kelvin. So it's still going to experience the exact same change in entropy. But we're changing some of the other stuff. Specifically, what's different about B? B is still losing 10 joules, but what's different? Right, it's at 301 Kelvin. So previously, the temperatures were very different. Now the temperatures are very close to each other. So we do that division, negative 10 divided by 301, and we get negative 0.0332 joules per Kelvin. So since B is at a lower temperature, it's losing more entropy. The change in entropy is inversely proportional to the temperature. If we go back to the formula we've been using for delta entropy, higher temperature means less change in entropy per unit of heat. Whereas if B is at a lower temperature, 301 instead of 350, it's experiencing a larger change in entropy as a result of those 10 joules. So if we add those together, what's the new delta S total going to be? Would that be positive, negative, or 0? Yeah, positive 0.0001 joules per Kelvin. So entropy is still increasing overall. This still follows the second law of thermodynamics. The closed system has entropy that is not decreasing. In fact, it is increasing. But what do you notice about that change as compared to the previous one?
It's less.
Yeah, it's a much smaller change. And why do you think that is? Why does case 2 involve a significantly smaller change in entropy than case 1 did?
The objects for case 2 are closer in temperature.
Yeah, if you've got objects that are really close to each other's temperatures already, the change in entropy is going to be pretty small because it's not much of a difference. But if the objects are very different in temperature, then the same change, the same flow of heat, results in a much larger change in temperature, in this case, 47 times as large. So that's an important thing to keep in mind. If two objects are close to the same temperature already, then exchanging heat will result in an overall a very small change in temperature, very small change in entropy. And if the entropy is only increasing a little bit, it's fairly easy to put it back the way it was. It's fairly easy to undo that. But if the entropy is changing a lot, if there's a large increase in entropy, it's difficult to put that back the way it was. It would be difficult to make the heat flow the other direction. And you see this in everyday life with things like air conditioners and refrigerators. Naturally, heat is going to flow from where to where? Where would you, or which direction would you typically expect heat to flow?
From hotter to cooler.
Right. Heat is naturally going to flow from hot to cold. The purpose of an air conditioner is to actually reverse that. If you've got a building, let's say you've got a building, this is just some house or whatever, and let's say it is a hot day. So you've got a hot temperature outside, and you've got, or at least you would like, the air inside to be colder. Naturally, heat is going to flow from hot air outside to cooler air inside, making the inside of the building warm up. But let's say you want the inside of the building to get colder instead. You've got to take energy, thermal energy from inside the building and dump it somewhere else. So that means the air conditioner is a machine that makes heat flow in the other direction. The air conditioner makes heat flow from the colder region towards the hotter region. This is an unnatural flow of heat. We're making it happen by using this machine. But what's going to happen to entropy as a result of that? If you make heat flow from the cold region to the hot region, what would actually happen to entropy?
Would it decrease?
Well, let's take a look at it for each one individually. The inside of the building is heat entering or leaving the inside of the building?
It's leaving.
Right. And if heat is leaving, what happens to entropy?
It decreases.
Yeah, entropy decreases because heat is leaving. Meanwhile, heat is entering the hot air outside region. So that means the entropy of that region increases. They're exchanging equal amounts of heat. We've got the inside of the building losing heat and the air outside the building gaining the same amount of heat. So what does that suggest about the amounts of change in entropy? If you've got cold air, a low temperature, and you lose some heat, take a look back at the delta S formula. You've got the same amount of heat leaving the building and entering the air outside. But if you've got some amount of heat divided by a low temperature, what does that suggest about the amount of delta S?
It would be higher?
Yeah. If the temperature is cold, you're dividing by a small number, so you get a large result. So heat leaving the cooler air means entropy is decreasing by a large amount. Meanwhile, in the hot air outside, you've got the same amount of heat, but you're dividing it by a higher temperature. So what does that tell you about the result?
It would be lower.
Right, you get a smaller amount of entropy change. So the building is decreasing its entropy by a lot. The air outside is increasing its entropy by only a small amount. So if we add those changes together, if you have a large decrease plus a small increase, what would you say about the total entropy?
It's going to be a large amount.
Sorry, what was that?
It's going to be a large amount still.
Well, we're adding a large decrease plus a small increase. Are those going to combine or partially cancel out?
Oh, it's going to partially cancel out.
Right. But which one wins out? Do we end up with a medium increase or a medium decrease?
A medium decrease.
Right, because we have more decrease than increase, since the decrease is happening at a lower temperature. So the total entropy of this system decreases. Making heat flow in this unnatural direction from the cooler region towards the hotter region results in the overall entropy of this system decreasing. Is that possible?
No.
No? So air conditioners don't work?
Oh, sorry, yes.
I mean, we can certainly say from practical experience, yes, this does happen. Air conditioners do exist, thank goodness. But how does that square with the second law of thermodynamics? Does this violate the second law?
Yes, it does.
Looks like it, because this is a system where the total entropy is decreasing. But remember, the second law only applies to what sorts of systems?
Oh, it only applies to closed systems.
Right, and this is not technically a closed system. Even if this whole thing takes place, like let's say this whole thing takes place in a sealed, insulated warehouse, this still technically doesn't count as a closed system, because what does the air conditioner need in order to operate?
Needs air.
Well, there's plenty of air inside the system. That's not a problem.
Or heat.
And heat, it's basically making the heat flow. But do you have to plug in an air conditioner, or can it work on its own?
Oh, you need energy.
Yeah, that needs energy. You've got electrical wires coming in. That air conditioner has to be plugged in. And that means the air conditioner operates only because it's getting energy coming in, doing work from outside the system. That energy is coming from a power plant. So this alone does not count as a closed system. If we did include the power plant, we might call it a closed system. But the power plant is operating in a way that causes an increase in entropy, regardless of what type of power plant. If this power plant is, like, let's say this is a wind power plant, if you got a windmill, the wind hitting the windmill, at the beginning, the wind's all these molecules moving in one direction. That's low entropy. The air hits the windmill, makes it spin, converting that energy into electrical power. But those air molecules, instead of all moving in one direction, they're now scattered in various different directions. So that's higher entropy. So a wind power plant involves increase in entropy of the wind, increase in entropy of the air. Or let's say a wood burning power plant. If you're powering this power plant by burning wood, wood is low entropy. The hot smoke that comes off is much higher entropy. So no matter how you're getting this entropy, whether it's wind power, solar power, or burning something, or water wheels or whatever, any sort of power plant is going to involve an increase in entropy at the power plant. And that increase in entropy at the power plant is much larger than the decrease in entropy involved with the air conditioner. So using something like an air conditioner to make heat flow in the opposite direction from natural is going to decrease entropy locally, but it's got to be balanced out by an even larger increase in entropy somewhere else. So the total entropy of the universe is increasing as a result of this interaction.
Oh, okay. That makes a lot more sense.
And that's really the trade-off of the second law of thermodynamics. It is absolutely possible to locally decrease entropy. We do this all the time. In fact, some philosophers have said that life is all about local reversals in entropy. Life is all about some system locally decreasing its own entropy. But that's always balanced out by something else somewhere else, increasing entropy even more. Any other questions on that?
No, that's it. Thank you for the help.
You're welcome. See you later.
Bye.